Hello and welcome to this POP webinar. Today's topic is runtime correctness checking tools. I'm Joachim Protze from the RWTH Aachen University, and I'm happy to talk about two correctness checking tools that we are developing here in Aachen. Probably okay. Next slide works. When I talk about runtime correctness checking, then I mean tools that are able to detect correctness issues in parallel applications. And that means they run with the application. So the application runs under the control of the tool, and that allows the tool to detect such correctness issues during the execution. At the other side, that also means that the tools can only detect issues that are observable during this execution. And this is different from static analysis tools, which analyze the complete code base, and they will be able to detect issues that probably are not executed when you run it with a runtime correctness checking tool. That means to get the best of this runtime correctness checking tools, you should use a representative input data that triggers the code path that you would also use in your production run. The other point I want to point out is that the tools that I'm presenting today, they are optimized to provide you as few as possible false positive reports, and that might come at a cost that they sometimes omit some issues. But if they report an issue, then you can be quite sure that you really have an issue in your code. So the first tool is MUST. MUST is an MPI correctness checking tool. It's a scalable correctness checking tool. We use it to with applications that run with 16,000 processes. So you can really use this tool at scale. When in a more interactive setup, I would make this an interactive slide. I would ask you what are the issues in this MPI code. But here I want to just to use it to explain what kind of issues MUST can detect in an MPI code and what are the kind of reports you would get. So the first issue in this code is that we are calling MPI without calling MPI init. The next problem is that this code is using a Fortran data type. MPI integer is a Fortran type. The C type, the corresponding C type would be MPI int. So there is a Fortran type used in C code. Then the code has a deadlock. All processes try to receive data. They cannot finish the call because they will never receive the data. Then using this size minus rank, when you think about that twice, then you will realize for rank 0, size minus rank is size. And since the ranks in MPI are numbered from 0 to size minus 1, you will communicate out of scope of the communicator. Then this code defines a data type. So type contiguous is a constructor for a data type, but MPI requires you to also commit the data type. So call MPI type commit on this data type before using the data type. Also, this type is not freed before returning from main. This is not really an issue. So MPI does not require you to free the type before MPI finalize, but it's best practice. And if you would create types in a repeated, in an iterative fashion, then this would really create an issue, because then you're more or less leaking data, and at some point MPI might run out of resources. In case we ignore the deadlock here and the communication here really would happen, then this send operation would try to send 2 times 2 integer values. So this send would try to send 4 integer values, but the matching receive only is prepared to receive 2 integer values. Some MPI implementations will error out and having an error message, speaking of message truncation. Other MPI implementations might just crash or create buffer overflow. Then the last issue in this code is that before return, MPI requires you to call MPI finalize in each process, and this is also missing here. One issue that is not listed here, because this code is using synchronous communication, but if we would try to fix this deadlock using non-blocking communication, then we would also have what I call a data race in MPI. So the non-blocking communication would receive or send the same buffer as the receive, and so there is non-deterministic behavior which data would be sent or received. The good news is that most of the issues can be detected at runtime, and most of the issues will also be detected by the must tool that I'm talking about. The only two things, must needs MPI init and MPI finalize, so that must can start the execution, and in MPI finalize, must will do some additional analysis. And so those two function calls are needed in this example. So let's use this example, and let me show you how you would use must with this example. So the first thing is, of course, you need to compile the code, and I would always suggest that you compile the code with debugging symbols, so that must could also give you source line information for detected issues. The next step is, as a next step, you would execute your code, and in this example, I would execute the code with MPI exec on the local host and with 2 MPI processes. And to execute the code under control of must, just prefix your normal execution statement with must run -- must : MPI exec. This will start the execution under control of must. That means the must run script will print some information about the initialization before actually executing the application. So what do we see here? Without additional flags, and I will come back later to some of the available flags, without additional flags, must runs in the default mode, which is quite safe, but it does not scale, and it might be quite slow. A reason is that must in this mode is also prepared that the application crashes, and in case of a crash, this mode will make sure that must reports and collects all information that leads to the crash, and therefore must runs in a really synchronous way. And there are different modes that will run faster and scale better. Then the other thing is, depending on the setup and the installation of Must, can pre-build some of the infrastructure and basically cache that. And then Must will tell you, okay, for this execution, I'm using one of the pre-built infrastructure setups, or if for a combination of flags, no pre-built infrastructure is available, then Must will generate code on demand. Now, as I said on the last slide, the example has a deadlock, and the deadlock is the only case where the runtime analysis of Must will print out something during the execution. And the point is that Must will not modify the execution of your code, so it will not modify the MPI calls that are made, and that means Must just does the analysis, will detect that there is a deadlock or that there is a potential deadlock, but it will let the application run nevertheless. And that means after this message, the application is stuck in the deadlock. At the one hand side, it gives you the possibility to attach to the execution with a debugger, but you can also just hit Control-C to abort the execution at that point, or if you run Must in a batch job, then you should set a reasonable time limit so that the batch system kills the job, or you use some of the cancel calls to cancel the execution once you see in the log file that Must detected a deadlock. When Must finishes execution, or when the application finished execution, then the Must run script will also print you information on where to find the report. And in this case, the report is an HTML file, and you would open that HTML file in a browser. On some clusters, you can find a browser on the front-end nodes. On other clusters, you would need to copy the HTML file to your desktop. So what is in the HTML file? The report will always have a format like this. So the table shows us first which ranks, which processes or threads are affected by this issue. Then the type can be error, information, or warning. The message box gives you information on what is going on here, and in this case, it's a message about a type mismatch between the MPI integer type that is sent and the receive type that is MPI int. And so the two types are not matching, and that's the error detected here. Then the next column gives you information where the error occurred. In this case, it's the MPI send where the error was detected. You get also information about the source code line, and that's where the -G flag is important. And Must will provide you as much related information as possible. And so all the references listed here are also used in the explanation. And in this case, we get information about the involved send and receive because it's a type mismatch. And then also information on where the involved data types were created. If it's a communicator that was created by the application, then you would also get information about the communicator that was created. In some cases, you can find a hyperlink in the explanation text, and then you can just click on it and get to a different view. And in this slide, I'm showing you the graphical representation of the deadlock. And as I said initially, we have a deadlock between two MPI receives. In this example, I executed the code just with 2 processes, but even if I would execute the code with 8 processes, you would also just see a cycle so you would only see one dependency cycle, and Must tries to reduce this dependency graph as much as possible and only point out the core of the deadlock. In addition, what we see here is the communicators used in this MPI receive. That's MPI convert and the tag that was used. And in some cases of deadlocks, you will see that the tags do not match, and you might see a deadlock between MPI receive, MPI send, where you see, okay, there's something strange going on. Down here, you have a call stack view. As an example, is trivial. Also, the call stack is trivial. But if the deadlock comes from different parts of your code, then you would get a call stack that is merged as much as possible, but then diverges where the execution diverges. In the best case, you would see this green bar telling you, okay, Must did not detect any MPI usage errors during this run of the application. So to summarize, or to summarize how you use Must, you compile and link the application as usual. The important thing is that to use Must, you should link the application against a dynamic library of MPI, which is for most implementations the default. If that's not possible for your MPI implementation or for your system, then you will need additional steps. You should always use the debug flag for source code information. Then you either replace MPI exec with MPI must run, or as I showed earlier, just prepend your MPI exec command by must run must MPI exec, and that will work with any MPI exec command like srun or whatever. When the execution is finished, inspect the must output HTML, and additional files will be put into a must output directory. On systems that have GraphViz installed, the graphs that I showed you in the previous slide will be created automatically. Otherwise, you will only find dot files, and you need an additional tool to create images from those dot files if you want to look at them. An important thing is that must run will always allocate additional processes, and when you run the application in a batch system, you need to be aware of that fact because you need to allocate the extra resources. As a bit of background information, here an overview of execution under control of must. So what we see here is the application consisting of 4 processes here, and each of the processes uses 4 threads. So we have 4 application processes with 4 application threads. And in this diagram, we spawn an additional analysis thread for must, and we spawn additional 3 analysis processes for distributed and scalable analysis. And in Must, we distinguish the analysis that we do in 3 groups. Local analysis only need information that are available on the local process, on the local thread. These analyses are typically done on the application process. Then we have distributed analysis. They can run in this tree, in this communication tree, and they will either run just on this single level, or they are partially executed in a reduction fashion. So they run on each of the levels in the tree and complete the analysis on the root of the tree. Some analyses are unfortunately still centralized analysis. One of them is deadlock graph analysis, which is only used if a deadlock is detected to generate the graph that I have shown you earlier. Another thing is writing the HTML output is also done by this centralized node to synchronize the output and write everything into a single file. There are different flags to change the behavior of Must. I've already showed you the MPI exec flag. The Must no crash flag asserts that your application will not crash during execution, that allows Must to run analysis asynchronously, and therefore provides better scaling behavior. Then there is the Must info flag. This will not execute the application. It will just print you information about the combination of flags that you provide in addition, and will tell you how many MPI processes Must will launch for this configuration. So starting this setup, Must info will tell you, okay, in total you will need 7 MPI processes. And that's the number of tasks or MPI processes you need to reserve from the batch system. Then Must has 2 different flags to turn on distributed analysis. And only if one of those flags is available, then Must will create such a tree for the analysis. Otherwise, the tree will just consist of the application processes and a single centralized analysis node, and all the intermediate nodes in the tree will go away. And then finally, Must has a flag to allow hybrid analysis of multi-threaded applications. And with that flag, Must will spawn an additional analysis thread and will also be thread safe. To get to such a setup, you would need to use Must fan in 2 that tells Must to use a branching factor of 2, and the Must hybrid will tell Must, okay, there are threads in the execution. Okay, so now let's come to the OpenMP tool, and that is Archer. Archer is a data race detection tool specialized for OpenMP usage. It's based on existing data race detection tool called Thread Sanitizer, which comes with LLVM and GNU compilers. The runtime overhead is something between 2 and 20x, depending on the application behavior. And X really means 2 to 20 times the execution time of the application. Archer consists of a runtime analysis and a static analysis part. The runtime analysis part provides OpenMP synchronization semantics to the data race detection tool. The semantics is derived from the OMPT interface, which was added to OpenMP with 5.0. And the Archer runtime is delivered with LLVM since the LLVM release 10. And all the fixes and extensions to Archer are always pushed to the LLVM repository. So the more or less latest state of Archer will always be available in LLVM. But the other thing is also to get really the latest version of Archer, you also need to check out the latest version of LLVM. The static analysis in Archer was or is consists of a Clang compiler pass, which tries to identify race-free code and exclude this race-free code from runtime analysis, which would lead to reduced overhead. Unfortunately, the development is stalled and the compiler pass is not compatible with the latest Clang. So that's not in a state ready for use. Now, how would you use Archer? In this example here, I'm showing you a code that if you want to look at the code, we can put a link on the webpage later. But here I'm compiling the code as an OpenMP program, and then I'm executing the code with one thread to see what is the result for 0 execution, and that's the right result. So what the code does is it calculates the prime numbers between 2 and a million, and with 0 execution I get the right number, and then when I start the code with more threads, then I see the result is different, and that's always a good indication that there is a data race. So to identify the data race, I need to recompile the code, passing in the flag for thread sanitizer, and again the -g flag for debugging information, and compiling the code with thread sanitizer is sufficient, because then when I execute the code, the OpenMP runtime will automatically load Archer and provide me the OpenMP data race detection using Archer. So when we look at the output of Archer, then we can see, okay, there is a data race in this prime OMP file on source line 44, and the race was detected during a write of size 4, and the previous access was also a write of size 4. Now, when we look at the code, we can see, okay, so line 44 is this line, and looking at this line, we actually have 2 writes here. One write is the increment of total, and the other write is the assignment to primes. Now, the output here also gives us information about the colon of this column of this access, and if we would check out the code in an editor, then we would see, okay, the race was detected for this increment of total, and it's an obvious data race. We have an OpenMP for loop here. All the threads will check whether I is a prime number, and if they detect that I is prime, then they will try to increment total. So this is the more obvious and easier to detect data race. but depending on the execution and the hardware and the compiler and other factors, this code might also have a second data race in this line, and that's when the data race on total results on two threads getting the same result for this increment of total. That means for a specific schedule of the memory accesses, two threads might, for example, read total at the same time, get the same value, then do the increment, write back the same value to total, and then access the same element of primes, assigning their I. And in that case, we would have a second data race, and this is also a data race that Archer will detect. It will not be detected in all executions because the data race is possibly not observable in all executions. One last statement that I want to make here, and that's important from my perspective, because some publications try to introduce a notion that some races might be benign. That's a notion that probably comes from Java or other programming languages, but in C, C++, and also in OpenMP, there is no such thing as a benign data race. Any data race is undefined behavior or unspecified behavior, and compilers might do anything there, and the data race needs to be fixed. So again, summary, how to use Archer. What I've showed you in the example was how you would compile a C application with Archer. The same thing would also work with C++, just use Clang++. For Fortran, it's a bit more difficult because the Fortran support in LLVM is currently quite limited. So my suggested way to apply Archer to Fortran code, or even to mixed Fortran and C code, compile the Fortran code. That should be application.f. It's a Fortran application, but compile the Fortran application using gfortran, compile it as usually with OpenMP flag, add the sanitized thread flag. That's also available in gfortran, so that will instrument the code. But then for the linking, again, use the Clang compiler. For the linking step, you need also the sanitized thread flag during linking so that the runtime library is linked. When linking with Clang, you need to explicitly link in the Fortran, the GNU Fortran runtime library, and this flag might be necessary so that Clang picks up the right GCC toolchain. If multiple GCC toolchains are available on your system, then Clang might pick up the wrong toolchain. Right. With LLVM 12, you might also try and replace gfortran by the Flang compiler, but my brief experience with Flang is that Flang is more picky on the Fortran standard and will possibly result in more compiler errors for codes, for old and grown codes, which might rely on some things that gfortran supports, but are not standard compliant. Just a few important Archer flags. I would always suggest that you run the code with this tsend option, which disables analysis for non-instrumented runtime libraries. This flag is also quite important if you want to runs thread sanitizer or Archer with MPI applications, because MPI libraries are well known to expose memory access patterns which might be interpreted as data race by data race detection tools. So Valgrind has the same issue, but with that flag, those errors will not be reported. Then another nice flag is the ignore serial flag. This will turn off data race analysis for serial parts of the execution. So if you have a serial initialization that takes quite some time, then you can reduce the runtime overhead for this serial part. This is not on by default, because if you have, in addition to OpenMP threads, you might also have other threads in execution, and then it would not be a good idea to use this flag, because then you might really miss data races. You can disable loading the Archer runtime during execution by passing in the enable zero flag. For more flags or for documentation on more threads, just look into the Archer directory. There is a README file documenting all the available flags. Right, if you want to use this flag, then you need to make sure that OpenMP gets really initialized at the beginning of the execution, because only when OpenMP gets initialized, Archer will be started. And an easy way to make sure that OpenMP is initialized is to just call OMP get max threads at the beginning of the main function. Just a few known limitations of Archer. The support for OpenMP tasks has two known issues. One is for task dependencies. So Archer knows task dependencies, will not create false positives for task dependencies, but the current implementation of Archer might over adjust for dependencies, and especially when you have dependencies on non-sibling tasks, then Archer might miss some data races. This is something that will be fixed in LLVM 13, hopefully. And also for the concurrency of tasks, if tasks are executed on the same thread, currently Archer will not detect data races between those tasks, because the analysis is done on a threading level. But there is better tasking support on the way, and I also hope that this will be pushed into LLVM 13. A preview is available in my fork of LLVM, but this is something that we will upstream into LLVM. For OpenMP target regions, it's not possible to compile target regions for the GPU with thread sanitizer, but Archer can be used with x86 offloading. We have done that, and it works. You can find data races, but as I said, the code will not execute on the GPU. The code will execute on the host. In addition, if you use asynchronous target regions, then Archer might also miss some synchronization semantics of this target offloading, and then Archer might actually create false positives. For OpenMP reductions, they are a bit difficult for runtime analysis tools. And the current policy is to ignore memory accesses that are introduced by the OpenMP implementation to implement the reduction, but this might actually lead to the omission of data races. And I think for LLVM 13, we will add a flag where you can turn off this reduction handling, potentially get more reports, but we will not miss data races. Okay, As the last slide, I want to show you an outlook on how we plan to incorporate MUST and Archer so that you can use it for hybrid analysis of MPI plus OpenMP codes. This is also available on the MUST website for download. So we have this feature preview available on the website. This has two new analyses. One is data race detection analysis for MPI. It will allow you to detect data races of MPI buffers with memory accesses done by other threads, or data races in the MPI buffer accesses. So when you have multiple MPI communication on the different threads, they all access the same buffer, then this will be detected with this extension. It also enables race detection for non-blocking communication. If a thread accesses the buffer used in non-blocking communication while it's semantically passed to the MPI library, we have an implementation that also detects data races in one-sided communication. This is something that currently does not scale very well. That's actually not part of this preview, but will be pushed afterwards. But it builds on the same infrastructure. The output will be on the command line and redirected in a file. Okay, and the other analysis that is also enabled by this testing version of MUST is type matching for application view on buffers. That means if the application allocates a buffer as integer, but uses MPI double in a communication, then this is something that this analysis will be able to detect. And as a side effect, this can also detect buffer overflows. So if the buffer that you pass into MPI communication is too small to actually be used for the pattern that is described in a MPI communication call, then this will be also detected. This feature is implemented as a Clang optimizer pass. So you need to compile the code with Clang, and therefore it's not available for Fortran codes right now. And both features rely on the LLVM compiler and the LLVM OpenMP runtime. And so these two analyses are a bit limited to using LLVM. Okay, and with this outlook, I'm at the end of my presentation and look forward to questions. Okay, so there is the first question. Are debugging flags necessary in the case, or does MUST detect problems regardless of the flags passed during compilation? Okay, if you don't pass in debugging flags during compilation, then MUST will not be able to provide you source line information, but MUST will still detect the issues, give you the report, but the report will not include source line information, obviously. As a hint on where you might find the call, MUST indicates that was the nth call to this function. So it will, for example, report that this was the third call to MPI receive, and then that might already help to identify the call with the issue. The next question is, are type mismatches detected if the colliding types are of the same size? Yes, and I mean, that's what we already saw in the report. MPI int and MPI integer are of the same size. They are actually in some implementations the same type at all, but must will detect the issue. Another question is, are there any specific considerations for containers, for example, singularity? Okay, I don't know what this question is targeting at. I mean, I think you can run the code in any environment that allows you to execute MPI code. So you should be able to run that also in container environments. Next question is the extra process shared with the process of the application? Okay, I tried to interpret it and go back to the diagram. So when must starts this application with the corresponding flags, then must really executes MPI exec starting 7 processes, but must will hide those extra processes from the application, and therefore a normal MPI application will only see those 4 processes. And so whenever the application uses MPI convert for any purpose, must will replace MPI convert and replace it by the communicator for these 4 processes. And so the application has no way to see those extra 2 processes, and the application will also not realize that there are extra processes. Okay, the next slide is slide 10. What it is? Slide 10. Okay, that was also the diagram. In slide 10, is each must instance box a separate process? Right. So the question is each box a separate process? That means we won't need 1 extra process, but 2 to the power of n. No. So in this case, we would, in the worst case, we need double the number of processes. In the default layout, there is no extra process, so there are no intermediate processes. In the default layout, you only have 1 additional process, and all the processes communicate directly. And with the in the default distributed mode, we use a fan-in or branching factor of 16. That means we have for 16 application processes 1 extra process, and then potentially more if you need more levels in the tree. But that means we have about a 16th additional processes. So less than 10% more processes than the application. It depends a bit on the scalability and the communication behavior of the application. If the application does really frequent communication, then you probably get better results, or the analysis scales better if you use a smaller branching factor. If the application just communicates from time to time and does really computation in between of communication, then a branching factor of 16 is a reasonable approach, and that's why we have that as the default. on the other hand, when you think of a system like BlueJeanQ, unfortunately they are not there anymore. But on BlueJeanQ, it was a quite nice setup to use branching factor of a branching factor of 2 because of the communication, computation relations in the system. But on the BlueJeanQ, you always had partitions of powers of 2, and so if you wanted to run a normal job and just add MPI processes, you would need to run the next bigger allocation size with double the number of ranks or double the number of processes, and then you had enough processes to run with a branching factor of 2. Okay, the next question is it planned to add support for GCC or Intel compilers in the future? So you can use Archer also with GCC, and that's more or less what I showed you with the G-Fortran compiler. The thing is just that right now only the LLVM runtime has the OpenMP interface implemented. GCC is working on an implementation of the OpenMP interface, and as soon as that's available, there is no issue in using Archer with GCC. The problem with Intel compiler is that we depend on the compiler instrumentation done by thread sanitizer. So this is something that is implemented in the Clang and the GCC compiler. And the instrumentation there means for each memory access, for each load, for each store, the compiler instruments the code, adds calls into the thread sanitizer runtime, saying, hey, here is a read, here is a write, you want to analyze that. And this compiler instrumentation is not available with Intel, with the Intel compiler. That would be up to Intel to add the support for that, and then Archer could also be used with the Intel compiler. Okay, then next question. I would like to find a tool to confirm view the behavior of extra asynchronous progress threads in non-blocking functions. Is it possible to use must for this? So the support for multi-threaded applications is we started to work on that. It's a bit limited right now. For example, deadlock detection does not work right now for the hybrid use case because the deadlock analysis has no idea of the threading semantics. That means the analysis might report deadlocks where there are no deadlocks, and the deadlock analysis might also potentially miss deadlocks if they are there. I'm not sure. I guess you would get more false positives, but if there is really a deadlock, I guess must will detect that. But this is something we had some initial work on the deadlock detection, also for the OpenMP parallel use case, but that is nothing we have production ready and in a public version right now. Can you provide more details on the static analysis performed for data arrays detection in OpenMP programs in Archer? Right. So, as I said, the static analysis is nothing that is production ready. It's available in a repository. If there is interest, just send me a mail and I can point you to the details. There are also papers on that. What the static analysis does is basically two things. It can detect that regions of code are serial code, and that means the serial code will be completely whitelisted for the thread sanitizer instrumentation. So then Clang will not instrument that code, and also Archer, the static analysis will try to analyze loops for dependencies in OpenMP parallel loops. It uses the analysis is based on poly, which is a analysis part of LLVM for polyhedral loop analysis. And so if the static analysis can prove that there is no data race in a part of the code, then this code will be excluded from the runtime analysis just by not instrumenting the code. Okay, then the next question is, can you give us more information on scalability? First must, and also including Archer and hybrid. Okay, so for must, we did experiments with application code using different benchmarks, where we executed on a cluster with 16,000 MPI processes. In this setup, we performed full deadlock analysis, all the type matching analysis. I mean, when you go to scale, the critical things are the analysis you do that you cannot do locally. So all the local analysis is free for scaling. The critical thing is just what you need to do with global or kind of global information. And so the runtime overhead for this 16,000 process run was like 10% over the execution. And the scalability of Archer, so the Archer runtime analysis also scales quite well. The analysis is completely done in parallel, so the application executes in parallel with all the threads running. The only scaling overhead that we have observed at that point is for some applications which do shared reads, so they where all the threads read the same data, as in matrix vector multiplication, all the threads read the same vector. And in that case, we see some really severe runtime overhead, and there also the scalability or the runtime overhead increases with the number of threads. But for most applications, the runtime overhead is really more or less independent of the number of threads that you execute, going up to full node of more than 100 threads on a node. Okay, and I think with that, I'm through all the questions. So I thank everyone for participating, for your interest, and look forward to meet you at the next conference or the next webinar. Okay, thanks.